How are we doing, okay? Now, what is integral of differential of anything? Anything, right? So that's going to be, let me give you again a different color. Where are my colors? You see them? Ah, thank you. This is PV at temperature T, okay, and temperature T, minus PV at temperature P equals 0. PV at P equals 0, what is that? How about not? 0 is the incorrect answer. At pressure equals 0, what becomes, Jessica?
RT1.
RT. Because at pressure equals 0, we have ideal gas. What is PV ideal gas? RT. Yes, P would be 0, but V would go to infinity. That's why PV is not 0, because yes, P is 0, but the molar volume becomes infinity. And the product PV is equal to RT at P equals. Okay? Carmen, okay? So, this ideal gas equals RT. So finally, we come to the last expression that now is a cubic equation, a state-friendly expression for the departure enthalpy oh boy, not good. I was hoping we do also entropy completely today, but so H minus H ideal gas. Can you see orange good enough, or should I switch to white? Come on. At any temperature pressure is equal to PV minus RT, okay? And I have the integral became plus, okay. Okay, hold it, I messed up something here. There's a T. Yeah, there's a T in front, it's a minus in front. Minus T that, and that has a minus. So here I messed it up, please correct. This is going to be plus T of that. The T comes, I forgot to put the T from here, and it has a minus in front. Okay, do you see that? Christian? Okay, so, okay, I'm changing this thing. And so this comes with a minus, so minus minus makes plus, and I have the T. Okay. So plus, okay, I'll switch to plus integral from T comma 0 to T comma P. Let me write this part first, partial P. Minus pressure, dV. And one last thing, it's common to write things in terms of the compressibility factor, PV over RT. So if you factor RT out, this becomes PV over RT. What is PV over RT? 0.2 minus 1. And that is the final equation for general equation of state, cubic equation of state. This is 6427. So if you plug in Penn-Robinson for P and integrate, you can do it analytically. Then you get the expression I wrote at the very beginning, Penn-Robinson you get 6429. And also your text has the result for SRK. Okay, I don't have it here, but you, no, I don't have it in my notes, but you have it in your notes. In both cases, you can integrate another. So, are we clear, guys? Any questions? So it was a long derivation, but I hope you understood every step, and there were some key concepts. Okay, I will start on entropy. Obviously, I have less than 15 minutes. Let me think. We start, and yeah, 4:45 I'm supposed to end here. Okay. So we'll see how far we go. For entropy, we follow exactly the same path. It will be similar in many ways what we are doing, but the second step will be a bit different. Enthalpy for ideal gas only depends on temperature. Entropy for ideal gas depends on both temperature and pressure. So that will have to be a little bit different. So entropy. I will not redraw this picture, exactly the same path. Entropy for temperature and pressure. The function. You can do similar things for temperature and volume. And I'll just give you the result for those. So the starting point will be as it was for the enthalpy equation, that S, step 1, S at T2, P2 minus S at T1, T1 equals S at T2, P2 minus S at T2, 0. This is the first bracket, plus S at T2, 0 minus S at T1, 0. That's the ideal gas path, plus S at T1, 0 minus S at T1, T1. And the pertinent equation we're integrating is the ds as a function of temperature and pressure, which is 6219. Let me write it here. Which was ds. No, sorry, that was the temperature and volume. 19, let me get the 6220. ds equals Cp over T dt minus partial V with respect to T at P dB 6220. So, at this part, what is ds here on the first part? We have constant temperature. So if the temperature is constant, this goes away, is this minus partial V. So right here, ds is minus partial V with respect to T at constant V. Here, constant pressure. So this goes away. So I think orange will show better than this, right? ds equals Cp over T. Last part, again, we have constant temperature, so that goes away. So as in the first one, we'll have ds equals minus partial molar volume with respect to temperature at constant pressure. D. Here. So I can rewrite those guys as equals, huh?
I was thinking positive dp dt.
Let me just write the integral forms, okay? So it's going to be minus integral of partial v with respect to t dp conditions t2, comma 0, t2 p2 plus integral conditions t1, p1, t1, comma 0, t2, comma 0, t1, comma 0, t2, comma 0, 2 number 3 of Cp over T dt. And by the way, in this path, what are we? Ideal gas, right? At pressure 0, ideal gas. So that's the same as Cp star. So that is equal Cp star. This is Cp star over T. So I can write on the integral Cp star. And it's a function only of T Cp star. And then I have the last integral, which is minus integral. This goes from T1 P1 to T1 comma 0. The partial minus makes plus. Sorry. No, sorry, it's minus. No, it's minus. Partial B with respect to T. Oh, I didn't put constant B. Okay, so by the way, this is 6, 4, 17, 8. No, sorry, no, that's not. Let's continue. The next part is what we do with the ideal gas. Before we could write this as H ideal gas at T2 P2 minus H ideal gas at T1 P1. But I want to express it in terms of differences ideal gas T2 P2 T1 P1. What is this expression for ideal gas? For ideal gas, because I'll have this ideal gas, this becomes Cp star over T dt, and here V is RT over P. So partial V with respect to T is R over P. So this is minus R dP over P minus R dln P. So for ideal gas, this becomes ds ideal gas equals that minus R dP over P. Okay. Let's write what is step 2. H ideal gas at T2 P2 minus S ideal gas. How do I calculate? Again, I will have to follow a path. Follow the same path. Okay, you can rewrite it as following the same path for ideal gas as ideal gas at T2 P2 minus S ideal gas at T2 comma 0 plus S ideal gas at T2 comma 0 minus S ideal gas at T1 comma 0, and finally plus S ideal gas at T1 comma 0 minus S ideal gas at T1 P1. And I have this ds. So the first part is going to be integral. Here, temperature is constant, pressure changes, right? So that's integral from, okay, let's write T2, comma 0 to T2, comma P2. Since temperature is constant, the ds ideal gas is minus RdP over P. Yeah.
Right under step 1, is that supposed to be step 2, T1, P1?
Oh yeah. Please correct. Okay, I think I will repeat step 2 next time, but let me just write it for completeness and have it be digest. I don't want to go way over the speed limit. The second part is the temperature change, so that's integral from T1, comma 0 to T2, comma 0 of Cp star over T dt. Does this term bring familiarity? Yes. This is exactly the same as this term here. So this is that term. And then the last term is like this, minus R dP over P, and this goes from T1 P1 to T1, comma 0, which you can rewrite as the thing is, the P equals 0 terms, we can, but there is no, look at this, here's another key. There is no temperature dependence. So the next key thing is to rewrite this as simply integral 0 to P2 dP over P with a minus, and this is plus integral, we put the minus, there's an R here, okay, R dP over P, and this is of P1 to 0, okay? What is integral? Notice it's exactly the same function I have. If you have integral a to b of a function plus integral of b to c, the same function, f d whatever, f d whatever. What can you do with those integrals? Add them up. That's integral a to c. So I have the same function, okay? So that is going to be minus integral P1, P2 of R dV. Okay. Obviously, once I reach step 2, I think I went over the speed limit, so I will continue with step 2. But are we okay up to step 2 for the entropy? Juan, I'll be happy to answer any of your questions. But you understand what? I have to cover this one.
Yeah.
I can't answer questions what if something different during class. So I just don't anything that is I understand it,
Yeah.
please ask it in class.
Okay.
But anything that is further thinking, ask after.
No, it was just okay. So
Yeah, just for the next time. Huh?
what was the second one?
We're the same thing.
Hey, drive safe. Oh, Jessica. So, she didn't tell me like this right here.